Hello everyone, today we are going to talk about matrix factorization, which is widely used in recommendation systems. I'm Jingwei Shen. First, we are going to talk about what recommendation systems are and the basic idea of matrix factorization. And then we will introduce the two basic models for matrix factorization. First, look at recommendation systems. The problem is that we have some users and items, and we observe the ratings of users on some items. But most of them are missing, so we want to make predictions about the unknown ratings. The problem can be considered as a matrix implementation, where we observe some elements of the matrix, and then we want to make predictions for the others. One possible method is to use matrix factorization. As the name suggests, matrix factorization is to factorize the matrix, which means we want to find out two or more matrices, such that when we multiply those matrices, we will get the original matrix. For recommendation systems, we are going to find P and Q, such that P times Q transpose is our predictions for ratings, and R is the observed matrix which we are going to implement. The idea behind matrix factorization for recommendation systems is that we find latent vectors that characterize the natural properties of users and items. So we assume the ratings are governed by the latent vectors. As we mentioned before, we want to make our predictions as close as possible to the observed ratings. So what we are going to do is to minimize the square loss. Here Pi is the latent vector for user I, and Qj is the latent vector for item j. So Pi times Qj transpose is the predictions for the rating of user I on item j, and Rij is what we observed, the true ratings. Well, it is not enough to just minimize over square loss, because we want to avoid overfitting, so we should add some regularization terms. One way to add the regularization term is to give penalty on the L2 norm of the matrix P and Q. Of course, there are other regularization terms we could use, such as a penalty on the rank of P and Q, but the L2 norm is usually the well accepted one. R hat is our prediction matrix, as we introduced. So further study revealed the relationship between R hat and the L2 norm of P and Q. The fact is that since R hat equals to P times the transpose of Q, the trace norm of R hat equals the L2 norm of P plus the L2 norm of Q. The trace norm of a matrix is the sum of the singular values of the matrix. So by doing so, we could we could change the criterion function into this form. We minimize over the trace norm of R hat plus C a constant times the max of 0 and 1 minus Rij times R hat ij. For simplification, we assume that the elements of matrix R is either 1 or minus 1, which means users will like the item or dislike. So the trace norm of R hat can be considered as a regularization term, and the max of 0 and 1 minus Rij times Rij hat can be considered as the loss function. If we predict the ratings correctly, the loss will be 0, otherwise it will be 2. Why need we do so? The reason is that the original criterion function is not a convex function. However, in this form, it is a convex function of R hat. So we could use some good properties of convex function to learn this model. We could transform it then into a SDP, semi-definite programming. So that's why we transform it into this form. And then we are going to introduce probabilistic matrix factorization. It has this form. The graph below, I think, demonstrate the models briefly, where the true ratings Rij equals Vj times Ui, the latent vectors, and all of them has a Gaussian distribution. And we want to maximize over the likelihood function. It turns out that we are in fact minimize E, which equals to the sum of the square laws plus some regularization terms. PMF in fact gives us some probability theory of the matrix factorization method. And for the learning part, we could use the following two methods. One is stochastic gradient descent. We see it is the criterion function is a function of u and v, so we randomly pick up ui or vj, and we use gradient descent update function to update them. It can deal with large data efficiently. Another way is to use alternative least square method, known as ALS. The reason is that the criterion function is not a convex function of v and u, but if we fix either of them, it is a convex function of another. So we fix u and optimize over v, and then we fix v and optimize over u. We do this alternatively and repeatedly until the criterion function reaches convergence. There are some extensions for PMF. One is the Bayesian approach, where we assume, we can see the right figure, where we assume that the parameters of v and u also have a Gaussian distribution governed by hyperparameters. Bayesian PMF will help us to learn the model better, because the hyperparameters will govern how much penalty we add on the regularization terms, and also time latent factor. In this method, we don't factorize the matrix into 2 matrices, but into 3. We're adding temporal informations. So by doing so, we could deal with the problem by adding some temporal information, which will give good performance in some applications. And here are some references papers. If you are interested in matrix factorization, you could read them. Thank you very much.